Welcome to this explainer. Today, we're doing a complete engineering teardown on one of the most critical and honestly most feared fault nodes in a hybrid dual-motor power control system. We're talking about phase voltage and PWM control loss. This isn't just some minor glitch, it is a catastrophic bottom-layer modulation failure. We're going to dive deep into exactly how it happens, how the system diagnoses it in literal microseconds, and the extreme engineering lengths we go to just to prevent it.
Picture this. An EV is cruising at highway speeds. What actually happens if the inverter's central nervous system, the signals controlling the motor's power, just suddenly misfires? It brings up that visceral fear of phantom unintended acceleration. When pulse width modulation, or PWM, loses control, the incredibly delicate electromagnetic balance of the stator is instantly destroyed. It's an electrical nightmare that could literally force a vehicle right out of its lane.
So let's clearly define the villain of our story here. PWM control loss is categorized as a severe ASIL D hazard. And for those familiar with automotive safety, you know ASIL D is the absolute highest risk classification there is. This fault directly wrecks the dynamic modulation accuracy of the inverter bridge. If those PWM pulses distort, your beautiful three-phase sine wave voltage collapses. You get severe asymmetric voltage, wild torque instability, and massive overcurrents. The stakes are truly life or death.
Okay, let's dive into how we stop this. We're going to look at a 5-dimensional safety shield. First, a deep dive into the fault's root cause. Second, microsecond hardware and software co-diagnostics. Third, design prevention controls, or DFMEA. Fourth, locking down process quality with PFMEA. And finally, the ultimate DVP&R production validation.
Section 1. The Fault Root Cause Deep Dive. Let's zoom way in to look at the micro-level physics of this failure.
In a high-frequency, closed-loop system, this electrical chaos usually triggers from 4 physical dimensions. First, you've got GTM timer glitches and clock asynchrony in the main MCU. Second, silicon carbide, or SiC, switching delays and thermal drift, where heat or tiny connector wear causes gate charge loss. Third, high DVDT ground bounce, which is massive common mode noise injected by switching speeds over 10 kilovolts per microsecond. And fourth, resistor drift and leakage in the analog front end, usually from high temps or moisture.
So, how do these microscopic phenomena actually ruin our day? Well, that high dV by dt ground bounce makes the ground potential jump violently, causing a 0-volt signal to look high, which triggers a microsecond cross shoot-through, basically firing the upper and lower bridges at the same time. Not good. GTM asynchrony flips logic bits, creating dangerous narrow pulses. Silk thermal drift slows down gate charging, entirely distorting your duty cycle. And that AFE leakage? It tricks the brain into thinking it's outputting one voltage when it's actually doing another, causing severe PWM duty cycle offsets.
Section 2. Microsecond software and hardware co-diagnostics. Think of this as the system's ultra-fast autonomous reflexes.
When things go wrong, speed is absolutely everything. The fault-tolerant time interval, or FTTI, for an ASIL D hazard is under 60 milliseconds, but the hardware reflexes, they have to be way faster. If the hardware detects the dead time between high and low side signals dropping below just 1 microsecond, the GTM hardware bypasses software entirely. It strictly blocks the PWM in under 10 microseconds. It's a hard, instantaneous reflex designed to save the inverter.
To catch this, the system runs continuous layers of defense. We have highly isolated ESD ADC sampling chains running at a blazing 10 MHz just to filter out common mode interference. Then there's the PWM plausibility check, constantly calculating the math between predicted and actual phase voltages. If it sees a 10% mismatch lasting over 2 milliseconds, it flags a fault. Plus, smart gate driver chips, like the UCC 5880-Q1, are doing microsecond cross-checks to ensure the PWM command actually matches the physical voltage at the gate.
But what happens when a defense is triggered? The fallback strategy depends entirely on motor speed. At high speeds, say over 7,200 RPM, you can't just shut it off. That causes uncontrolled power generation and massive overvoltage. It's like trying to instantly halt a runaway train. Instead, it uses a stepwise active short circuit. It shorts 2 phases to absorb the shock, then 1.5 milliseconds later shorts all 3 lower arms to safely clamp the voltage. At low speeds, under 2000 RPM, it just uses an active open circuit to safely freewheel to a stop. Section 3. DFMEA Design Prevention Controls. Let's shift gears and look at engineering the actual blueprints. We upgrade the blueprints to be bulletproof. Step 1. Applying GTM register locks and hardware parity. Why? To physically protect against logic bit flips caused by, believe it or not, cosmic ray neutron strikes. Step 2. Designing low-inductance laminated bus bars to suppress high-frequency overvoltage spikes. Step 3. Locking down the analog front-end bill of materials to mandate Class 1 C0G ceramic capacitors. These specific caps have virtually zero temperature drift from -55 to 125 degrees Celsius, which keeps our sampling data perfectly true.
And speaking of those laminated bus bars, 15 nanohenries, that is the magic number. It is the absolute maximum stray inductance allowed in the design, though the goal is closer to 10. Keeping the total parasitic stray inductance under 15 nanohenries is absolutely crucial to forcefully suppress those high-frequency overvoltage transients during extreme switching events.
Section 4. PFMEA Process Quality Lock. Now, let's step off the blueprint and secure the assembly line.
You can have a flawless design, but if the factory messes it up, it still fails. So manufacturing controls are rigid. Every single board gets 100% 3D X-ray or acoustic scanning. Fastening the high-voltage bus bars isn't left to humans. It uses high-precision torque angle servo screwdrivers paired with optical character recognition that guarantee the bolts have the exact right phosphate coating, keeping contact resistance under 5 milliohms. Finally, end-of-line automated calibration injects reference voltages to write perfect zero-offset correction factors right into the EEPROM.
To put that 3D X-ray inspection into perspective, the absolute maximum total voiding rate allowed in the solder joints is 5%, and no single void can be larger than 1%. If a unit hits 5.1%, the manufacturing execution system physically locks the track and isolates the unit. Zero tolerance. This stops thermal fatigue cracks before they can ever form in the real world.
Section 5. DVPR Ultimate Production Validation. Time for the torture tests. The validation standards here are just wild. Look at the vibration and thermal tests. 500 hours of 3-axis random vibration while cycling from -40 to 150 degrees Celsius, doing high-power switching the whole time. The passing grade? Not a single control signal interruption longer than 1 microsecond. Then, hardware-in-the-loop fault injection. They spin the motor on a dyno to 12,000 RPM under full load and intentionally inject a sub-1 microsecond dead time fault. The system has to catch it and clamp the voltage safely under 720 volts and 550 amps using that stepwise short circuit.
All of this intense engineering brings us to a final thought. As we've seen, phase voltage anomalies and sudden PWM shifts dump massive dynamic, thermal, and electrical stress onto a closed-loop system. To truly conquer this, engineering teams have to build dynamic simulation models that link asymmetric distortion directly to thermal loss transients. So, are you ready to model your transient thermal safety boundaries? Because in the world of high-voltage propulsion, knowing your exact diagnostic time window before thermal destruction hits isn't just best practice. It's the only way to guarantee ASIL D safety. Thanks for joining me on this explainer. We'll see you next time.